The following outline is provided as an overview of an topical guide to object recognition. Object recognition, a Euro task of finding and identifying objects in an image or video sequence. Humans recognize a multitude of objects in images with little effort, despite the fact that the image of the objects may vary somewhat in different viewpoints, in many different sizes and scales, or even when they are translated or rotated. Objects can even be recognized when they are partially obstructed from view. This task is still a challenge for computer vision systems. Many approaches to the task have been implemented over multiple decades. Approaches based on CAD-like object models, edge detection, primal sketch, Ma, Moen and Navasha, Low, Olivier Federers. Recognition by parts equals, generalized cylinders, Gions, Dickinson, Forsyth and Ponce. Appearance-based methods, use example images of the objects to perform recognition. Objects look different under varying conditions. Changes in lighting or color, changes in viewing direction, changes in size/shape. A single exemplar is unlikely to succeed reliably. However, it is impossible to represent all appearances of an object. 1. Edge matching. Uses edge detection techniques, such as the canny edge detection, to find edges. Changes in lighting and color usually don't Euro unregistered trademark T have much effect on image edges. Strategy. Detect edges in template and image, compare edges images to find the template, must consider range of possible template positions. Measurements. Good Euro count the number of overlapping edges. Not robust to changes in shape. Better Euro count the number of template edge pixels with some distance of an edge in the search image. Best Euro determine probability distribution of distance to nearest edge in search image. Estimate likelihood of each template position generating image. 2. Divide and conquer search. Strategy. Consider all positions as a set, determine lower bound on score at best position in cell. If bound is too large, prune cell. If bound is not too large, divide cell into subcells and try each subcell recursively. Process stops when cell is Euro or small enough Euro. Unlike multi-resolution search, this technique is guaranteed to find all matches that meet the criterion. Finding the bound. To find the lower bound on the best score, look at score for the template position represented by the center of the cell. Subtract maximum change from the Euro center Euro position for any other position in cell. Complexities arise from determining bounds on distance. 3. Grayscale matching. Edges are robust to illumination changes, however they throw away a lot of information. Must compute pixel distance as a function of both pixel position and pixel intensity, can be applied to color also. 4. Gradient matching. Another way to be robust to illumination changes without throwing away as much information is to compare image gradients. Matching is performed like matching grayscale images. Simple alternative, use correlation. 5. Histograms of receptive field responses. Avoids explicit point correspondences, relations between different image points implicitly coded in the receptive field responses. Swain and Ballard, Skyhill and Crowley, Lind and Lindberg. 6. Large model bases. One approach to efficiently searching the database for a specific image to use eigenvectors of the templates. Model bases are a collection of geometric models of the objects that should be recognized. Feature-based methods. A search is used to find feasible matches between object features and image features. The primary constraint is that a single position of the object must account for all of the feasible matches. Methods that extract features from the objects to be recognized and the images to be searched. Surface patches, corners, linear edges. 1. Interpretation trees. A method for searching for feasible matches is to search through a tree. Each node in the tree represents a set of matches. Root node represents empty set, each other node is the union of the matches in the parent node and one additional match. Wildcard is used for features with no match. Nodes are Euro at pruned Euro when the set of matches is infeasible. A prune node has no children. Historically significant and still used, but less commonly. 2. Hypothesize and test. General idea. Hypothesize a correspondence between a collection of image features and a collection of object features, then use this to generate a hypothesis about the projection from the object coordinate frame to the image frame. Use this projection hypothesis to generate a rendering of the object. This step is usually known as back projection. Compare the rendering to the image, and, if the two are sufficiently similar, accept the hypothesis. Obtaining hypothesis. There are a variety of different ways of generating hypotheses. When camera intrinsic parameters are known, the hypothesis is equivalent to a hypothetical position and orientation pose for the object. Utilize geometric constraints. Construct a correspondence for small sets of object features to every correctly sized subset of image points. 3 basic approaches. Obtaining hypotheses by pose consistency, obtaining hypotheses by pose clustering, obtaining hypotheses by using invariance. Expense search that is also redundant, but can be improved using randomization and/or grouping. Randomization, a section examining small sets of image features until likelihood of missing object becomes small, a section for each set of image features. All possible matching sets of model features must be considered. A section formula. 1 WC, K equals Z. W equals the fraction of image points that are a good C equals the number of correspondences necessary, K equals the number of trials, Z equals the probability of every trial using 1 incorrect correspondences. Grouping, a section if we can determine groups of points that are likely to come from the same object, we can reduce the number of hypotheses that need to be examined. 3. Pose consistency. Also called alignment, since the object is being aligned to the image, correspondences between image features and model features are not independent of geometric constraints. A small number of correspondences yields the object position the others must be consistent with this general idea. If we hypothesize a match between a sufficiently large group of image features and a sufficiently large group of object features, then we can recover the missing camera parameters from this hypothesis. Strategy. Generate hypotheses using small number of correspondences, project other model features into image and verify additional correspondences. Use the smallest number of correspondences necessary to achieve discrete object poses. 4. Pose clustering. General idea. Each object leads to many correct sets of correspondences, each of which has the same pose. Vote on pose. Use an accumulator array that represents pose space for each object. This is essentially a Huff transform. Strategy. For each object, set up an accumulator array that represents pose space each element in the accumulator array corresponds to early bucket in pose space. Then take each image frame group, and hypothesize a correspondence between it and every frame group on every object. For each of these correspondences, determine pose parameters and make an entry in the accumulator array for the current object at the pose value. If there are large numbers of votes in any object unregistered trademark S accumulator array, this can be interpreted as evidence for the presence of that object at that pose. The evidence can be checked using a verification method. Note that this method uses sets of correspondences, rather than individual correspondences. Implementation is easier, since each set yields a small number of possible object poses. Improvement. The noise resistance of this method can be improved by not counting votes for objects at poses where the vote is obviously unreliable, a section for example, in cases where, if the object was at that pose, the object frame group would be invisible. These improvements are sufficient to yield working systems. 5. Invariance. There are geometric properties that are invariant to camera transformations, most easily developed for images of planar objects, but can be applied to other cases as well. 6. Geometric hashing. An algorithm that uses geometric invariance to vote for object hypotheses, similar to pose clustering. However, instead of voting on pose, we are now voting on geometry, a technique originally developed for matching geometric features against a database of such features, widely used for pattern matching, CAD/CAM, and medical imaging. It is difficult to choose the size of the buckets. It is hard to be sure what a euro enough a euro means. Therefore there might be some danger that the table will get clogged. 7. Scale invariant feature transform. K-points of objects are first extracted from a set of reference images and stored in a database. An object is recognized in a new image by individually comparing each feature from the new image to this database and finding candidate matching features based on Euclidean distance of their feature vectors. Low. 8. Speeded up robust features. A robust image detector and descriptor, the standard version is several times faster than SIFT and claimed by its authors to be more robust against different image transformations than SIFT, based on sums of approximated 2D Haar wavelet responses and made efficient use of integral images. BAL equals bag of words representations equals. Genetic algorithm. Genetic algorithms can operate without prior knowledge of a given dataset and can develop recognition procedures without human intervention. A recent project achieved 100% accuracy on the benchmark motorbike, face, airplane and car image datasets from Caltech and 99.4% accuracy on fish species image datasets. Other approaches. Applications. Object recognition methods has the following applications. Surveys, Danielides and Eklund, Edelman. Raff, Peter M. and Winter, Martin. See also, AI effect, histogram of oriented gradients, OpenCV, scale invariant feature transform, Scalapedia article on scale invariant feature transform and related object recognition methods, SURF, template matching, lists, list of computer vision topics, list of emerging technologies, outline of artificial intelligence. Notes. References, Al-Gamal, Ahmed CS 534, Computer Vision 3D Model-Based Recognition, Department of Computer Science, Rutgers University. Hartley, Richard and Zisserman, Andrew Multiple View Geometry in Computer Vision, Cambridge Press, 2000, ISBN 0-521-62304-9. Raff, Peter M. and Winter, Martin. A Euro-OE Survey of Appearance-Based Methods for Object Recognition. A Euro, Technical Report ICGTR 01/08, Inst. For Computer Graphics and Vision, Graz University of Technology, Austria. January 15, 2008. Collins, Robert. Lecture 31, Object Recognition, SIFT Keys, CSE 486, Penn State. IPRG Image Processing, Online Open Research Group, Christian Szegedy, Alexander Toshev and Dimitru Erin. Deep Neural Networks for Object Detection. Advances in Neural Information Processing Systems 26, 2013. Page 2553-2561. External links.